And so, two topics for today. So the first one, the first one is inversion recovery, and so that's a particular kind of a pulse sequence that can be used for several different things. So one of the things it's used for is for trying to increase the contrast between two tissue types. That's a common thing that it's used for. But it's also used for perfusion imaging. And so MRI is quite flexible. So you can record the blood oxygenation, or you can record T2, blood oxygenation is T2 star, or you can record T2 or emphasize T1 or proton density. But you can also look at diffusion, so microscopic diffusion, or perfusion, which means like the actual flow of blood. And so inversion recovery is used for perfusion. So basically you sort of do an inversion recovery and label some spins, and then they sort of go up through the blood vessels into the brain, and then you can actually record how much blood flowed into the brain. And so that's another thing that inversion recovery is used for. So we'll talk about that. No echo, that sort of complicates it. And then we'll go over SpinEcho. So we kind of already went over SpinEcho, but that was just for the echo amplitude. So remember we had a SpinEcho equation that boiled down to e to the minus te over t2. So that was for the echo amplitude. But what we want to now do is get an equation that basically takes the T1 and the T2 and the proton density, all into account. And so this is like the equation that describes essentially what the final contrast in the image is. And so it's a little more than just e to the minus te over t2. So let's start off with inversion recovery. And so inversion recovery, so remember for SpinEcho we did a 90 and then a 180. And inversion recovery is just a 180 and a 90. So why is it called inversion recovery? So it's called inversion recovery because if we start off with our magnetization in the z direction, so we're at equilibrium like this, and then we do a 180 degree flip down to here, that's kind of the definition of an inversion recovery. And so since this direction is magnetization transverse, and this direction or this direction is magnetization longitudinal, that's negative longitudinal magnetization. If you do a perfect 180, you don't see any signal, you don't see any transverse signal. And so what will happen in that case is the magnetization so you'll flip the magnetization without changing its length, and then it will slowly recover through zero and then back up to the equilibrium. So we're starting, this right here is the MZ0. So that's the starting magnetization. And so that's hence the name inversion recovery. So you invert and then it recovers, and recovers but it has to start negative and go through zero. So if we just write out the simplest case of it and just try to figure out where we get to the steady state. So it looks like about half for pulse sequence, half for equations. Okay, so here's our pulses. So here's our 180. And then the timing doesn't have to be the same between our 180 and 90 and the next 180. And typically there could be quite a large gap, but I'll just make a slightly bigger gap. Slightly less bigger gap just to give me room for the equations. Okay, so here's another 180, and then another 90 here, and then etc. Okay, and so the time here. So this time, between when things repeat is our TR. And so there's no TE because we're not collecting any echoes. And so this time is typically called it's unfortunate that it looks a lot like a 1, but this one is called time inversion. And sometimes, if you read in papers, this one is called TD for time delay. Siemens apparently patented TD. They patented the use of, they prevented GE from doing a particular pulse sequence because it involved a patented time delay. So obviously you only really need TR and TI because TE is just dependent on it's just TR minus TI. So now what we want to do is just look at just the longitudinal magnetization, because remember a lot of what we're doing is we're manipulating the longitudinal magnetization, doing various stuff to it, and then we do a 90-degree pulse to make something that we can record. But the amount of stuff that we get to record is mainly due to what was done with the invisible longitudinal magnetization. So if you make a nice big, let's make these time points. And so what we're looking at is just the longitudinal magnetization, just a Z component. And so if we start, it's about halfway. Okay, so here's 0. So if we start off like this at MZ0, and this is ML, longitudinal magnetization. So when we do our inversion, what we'll do is we'll basically just go down to here. So our longitudinal magnetization will be negative. Now that can't happen with the transverse magnetization, because the transverse magnetization is always, since it involves x and y, and x squared plus y squared square root of that is the length of that, that thing is always positive. But the longitudinal can go negative. So if the longitudinal, where does the negative go to in the transverse case? Well, it sort of is incorporated into the angle, right? So the angle, can effectively make the transverse flip its sign, but generally you just think of the transverse as a positive number, and then it's got an angle that can sort of flip it around. So as soon as we go down there, we start to recover, and we recover, up to some point. So let's just draw our recovery up to here like that, and so that would be described by the Bloch equation, which we'll do off to the right here. And now we do a 90, and so now, if it's a perfect 90, then we'll get back to 0, longitudinal magnetization, all transverse. And then we continue to recover, and so for some period of time. And I'm not drawing it completely to scale, so you could have all these things could be slightly different times. So let's recover up to, so here's where we're recovering up to. That's the magnetization. This guy, the equilibrium, remember, is just the total number of protons and the Tesla. So now we recover up to say here, and now we do another 180, and so now this is going to be different. It won't go down to where it was. It will flip the amount that we've got now, but that's less than the total amount that we started with. And then we're going to recover up. But now, remember, here's where we started recovering from last time, was down here. But now we're recovering from a higher point. And so we're going to recover a little bit more. So this guy, here's where we would have been last time, but we're going to recover a little bit more because we started a little higher. So we're going to recover up to that guy instead, because we weren't quite as negative. And then we do another 90 degree, and after this, everything is the same. It's actually, I looked at my video from last year. It's actually already the same at this point. Steady state here. Meaning that from now on, nothing will change. So if you just keep doing this sequence, keep the TR the same and the TI the same, once you get to this point, nothing's going to change. You'll get the exact same thing every time. Assuming you have perfect 90 degree pulses, which of course you don't, but that's it's important to. So only the first one will have this lower amount of recovery. So now what we want to do is just go through the Bloch equations to try to figure out how much longitudinal we're going to have. So our bottom line is we're at a steady state here, but we're still not recording anything here. Here's where we start to when we do this flip is where we get some transverse that we start to record. So what we really want to know is how much longitudinal do we have at this point, which is going to explain how much transverse we get after we do the flip. So that's what we're trying. That's the goal, is try to figure out the equation for the amount of transverse we have here before we do the flip. And then there's going to be yet a different little thing added onto that if we do an echo, but we'll leave the echo out for now. Okay, so what's the equations for that guy? So if we start off at point 1. So where is point 1? So here's point 1 down here. So what's the equation? What's the Bloch equation for the MZ? So what we want is I got an MZ0, but yeah, it's not supposed to be. Yeah, I just fixed it right there. No 0. So what is the longitudinal magnetization ML? And so basically what it is just the negative of the equilibrium. So the longitudinal magnetization is just equal to the negative of the MZ0. So that was just our flip. And that's what an inversion pulse will do. If it's a perfect inversion pulse, it just takes the negative of whatever the current longitudinal is. So now we have to allow it to recover. And so what we want now is like time 2, which is like right before we do the flip. And so now we're going to run the Bloch equation solution, and what is that going to be? So it's going to, there's two parts to the Bloch equation solution. Remember, there's the first one minus e to the blah, and then plus the starting magnetization, if there is any, longitudinal magnetization times e to the blah. And so what is that going to work out? That's going to work out to that equilibrium magnetization times 1 minus 2 e to the minus ti over t1. So where did the 2 come from? So the two came from the second term, because our boundary condition is that the second term we're starting off with negative mz0, and so we have to sort of plug that into the second term of the Bloch equation solution. But it just turns out to be the same as this term. And there's a negative coming from the fact that we're starting off with a negative mz0, and so then we end up with 2 times e to the minus ti. So ti is the amount of recovery time. So now that we have that, what do we do with that? We ignore it because we don't care. And why is that? Well, because we're going to blow away all the longitudinal magnetization now and turn it back to 0 with a 90-degree pulse. And so we don't need that. We don't need that equation. So now we have this recovery up here to get to our steady state. And what's the equation for that guy? So the equation for that guy is going to be just mz0. It's just the first Bloch term. So the first, because our starting magnetization is 0 for the second Bloch term. And the only complexity is that we've got minus TD, but what is TD? TD is just is TR minus TI. Did I do that right? TD is, oh man, there's another typo in there. Yeah, so TR minus TI is TD. Yeah, so this guy is just TD. We could use TD instead, but I'll just save one symbol. And then divided by T1. So I'm sorry about the I and 1. Okay, so that's basically just starting with 0, so there's no second Bloch term, recover for a TD, but TD is equal to TR minus TI. Okay, plus 0. That's the second Bloch term. Okay, so now what do? We just do another flip. So we were up to 3 over here, and now we're up to 4. And what is 4? Well, 4 is just the longitudinal just equals, minus the same. So mz0, 1 minus e to the minus tr minus ti divided by t1, parentheses. Okay, so that was just our 180. So that's how you do a 180 when you're running these equations. And so now we have to do this recovery because our bottom line that we are interested in is number 5 here, like right before. And so now we're going to have a negative number for our second Bloch term. So the first Bloch term is the regular one where it so mz is going to be the regular mz0 times 1 minus e. And this time right here is the ti time, so we don't have, this is the ti. So this one is minus time inversion over time tissue property T1. And then now we're going to have our second Bloch term, and it's a plus, but since we got a minus from here, because this amount basically will go into the first term of the first part of the second term. so basically it's going to be this whole thing. So it's mz0. That will be the amount of magnetization 0 plus, So, right after the start, right after the pulse has been done. So it's mz0 and then 1 minus c to the minus. You can see what the problem is. There's just, it quickly gets out of hand if you have more than like 2 pulses over T1. So that's the magnetization we're starting with, magnetization at 0 plus, and then it's the second Bloch term, the second part of it is multiplied by E to the minus Ti, however long that is, over T1. Okay, so that's starting to get a little messy, but you can mess around if you just multiply all these out. So, multiply all these out, and then remember that, you can, when you multiply two things, it's the same as adding their exponents. So, separate all this junk out, and then add the exponents, and then you can simplify it to get the final one. And so I won't do it here, but you should work it out just to make sure that you just go through the algebra, that these two things are equivalent. So basically it's mz0 times 1 minus 2, it gets a little simplified, minus ti over t1 plus e to the minus tr over T1. So what do we? So that's our final answer. So what is this? It's the amount of longitudinal magnetization, inversion recovery, no echo. Because if we waited some time for an echo, there's going to be some T2 decay. And so what do you use something like this for? What you use something like this for is trying to figure out, this is kind of like the bottom practical line after doing the math, all sort of like compressed down into the main point. And what is the main point? The main point is, what should we set like TI and TR to in order to maximize the contrast between two different tissue types that have a different T1? So that's really what this is for. You're just trying to figure out like what would be the optimal way to get the biggest amount of contrast between two different tissue types that have a different T1. What should we set the TI and the TR to maximize that contrast? Because you could easily end up with the exact same contrast between the two tissue types. They have a different T1. But if you set these TI and TR in certain ranges, you can end up with no contrast, and then there's no point. You can't see the gray matter compared to the white matter, for instance. And so that's really the bottom line of why these equations are important, because they tell you how to optimize your sequence to increase the contrast. And these are things you can change on the console. So you're sitting at the MRI console, you can change the TI. I'll turn it up a little bit. And the question is, should I? And so how would you figure that out? You would just take this equation, plug in 2 different T1s and then figure out what combination of TR and TI will be the best contrast, the best contrast meaning signal difference, and this is the signal. So this guy is the signal. It's basically it's going to be our eventual transverse magnetization signal. So, okay, so that's inversion recovery, no echo. So everybody good on that so far? So that's exactly what the homework assignment is about. Like, here's 2 different tissue types. What is the difference in signal we're going to get from those 2 different tissue types for this setting of of TR and TI. So this is a simple one. You can sort of see we're just substituting the Bloch equation. We write out the Bloch equation, and then we just throw it out sometimes if it's irrelevant. And then in this case, what we did is we just stuck this guy into the first term of that second. So this is like this is first term. The first part, not first term, first part of second term Bloch solution. Okay. So all good. So we'll move on to SpinEcho. Any other questions about this? Sort of you're starting to get a feel for like how to operate the equations. Yeah.
So to figure out the optimal TR and TI amplitude, you concluded by plot it and look at this difference and take a derivative and find the maximum.
You wouldn't necessarily have to take a derivative. You could just do something like subtract the 2 and then find a max. So subtract the 2. You can subtract the 2, get a vector of the subtractions, and then just find the maximum of that difference. It's a little more of a pain in the butt if you're doing it in 2D, because you have like say, TR and TI, or 3D, you got TR and TI and T2. And TE, the echo time. So, but yes, in the simple case, you could just subtract and then find the maximum. Okay, so now we'll finally get up to a full pulse sequence. So I'm going to write out the pulse sequence. I'm not going to explain all the parts yet, but we'll just write it out. So. And we'll get to the parts later. So here's the RF stimulation. So the RF stimulation is, for SpinEcho, is just 9180. So let's draw. So here's our 90. We'll draw it out like a sync. We'll talk about what a sync pulse is next time, but a couple times after this. But for now, we'll just do our 90 and 180. And so then we have to draw all the gradients this time. So this is a little more fiddly. So we might be doing a slice select pulse here, and a little fixer, and then we might be doing a slice here. So here's what that slice select pulse looks like. It's kind of a funky little one. We'll explain that later. So this is this is what we do for the Z gradient. And so when we start to look at how these imaging things work, you're fiddling with all the gradients at the same time. And so in order to see, we have a minimum of 4 lines to sort of explain what's going on. So we've got, the z gradient and then the y gradient. Okay, so here's the effective center of our RF pulse. And so what are we doing on the y gradient? Well, we're doing some phase encoding, so let's draw that in there without explaining it. And then we can actually sort of look over here at what signal we're getting out. So this is RF record. So we're doing a little bit of phase encoding, and then we're doing a rewinder, which is right side up because we did it before the 180, but we won't talk about that. And so then what's going to happen is the amount of time, so this is tau, and that amount of time later we'll get a spin echo. So at this point, we should recover back to T2. Wait, I left out a gradient. Sorry. Gx gradient. Okay. And here's the RF record. Okay, so what is going to happen in our RF record? Well, we get a big FID, which we'll throw away here. Not recording that. And then what will happen is when we do the 180, nothing happens if it's a good 180. And then basically we should get a spin echo over here. And then this number here is going to be e to the minus t over t2, not t2 star, because we did a spin echo. Okay, so then what will happen is we'll wait a long time. And how long are we going to wait? We're going to wait, maybe a couple seconds. So kind of a long time. So this is like a, for example, 2 seconds. So these times are shorter because remember spin echo times are about 1/10 of a second, 20th of a second or something like that. And so this is kind of a long time, and then we'll do it again. So here we go again. So here's another 90, and then there'll be another 180. So here's another 90 and 180, and then another, another echo. There'll be another echo there. So what is our definition of TR? So the TR is going to be in between these two 90s. So that's the where our whole sequence repeats. And then the echo time, this is going to be the echo time right here. The echo time is much, in real life, it's much smaller. It's only like a 20th of a second, whereas the TR is like 2 seconds or something, so it's a big difference. And I left out a few gradients. So we're going to also do a right side up pre-winder, and then during the echo, we'll have a gradient on. And so it's a gradient echo. So at this part of the gradient, we're messing up the, at this part of the gradient, we've messed up the spins, and now we're fixing the spins. They're both sort of positive because there's the 180 in between, but whatever. And so now we're fixing the spins, and halfway through we fix everything, and then we continue to damage them in the later part of the gradient, and so then the echo goes away. The echo gets shrunk down faster. So this is, e to the minus t over t2 star. Star star. Because we've got, it's dying away because we're not doing spin echo anymore, and we've got the gradient on also, and so it's kind of damaging it. Okay, so that's a full spin echo pulse sequence. And what we want to do now is actually write the equations for spin echo, including the echo time delay. And so to do that, what I'm going to do is I'm going to write it out. I'm going to just make a graph of the longitudinal magnetization. It's kind of like the one I made for the spin echo, the first graph. And we'll just draw it out, all the way over here to sort of like, so you can see like what the actual, actual thing looks like. So we start at the very beginning. We all start at MZ0. So this is, MZ0. It won't be MZ0 the second time around, but if we do a really long gap here, it can get back up to MZ0. But for the very first one, we just do our 90 like that, and then we do a 180 here. So basically we've got some recovery like that. And then we do a 180. And then we got a long time to recover. So let's put it over here. So here's what we're recovering to. I recovered a little bit too much there. Let's just recover a little bit less like that. Okay. Okay, so then we take the negative of it, and then we slowly recover. Up to about like that, not all the way. Okay, so now what we do is we do another 90, because that's this guy here. So let's put this guy there. And then we do another amount of recovery here. So we get a little recovery. And then we do a 180. And then we come through, and right when we go through 0 is when our echo is. So this is a confusing thing but just think about it. The longitudinal magnetization when we have an echo is 0. So there's no Z component. So if the spins started recovering longitudinally a little bit when you do the 180, they're now sort of negative, and then at the echo time they come back to 0. So right at the echo. So basically, this is the center of the echo. So the center of the echo, ML equals 0. And so that's what we want. What is the amplitude of that signal after this mess? That's what we're trying to figure out. So what are the times here? So this time is the tau time, and then there's another tau. And so this time right here is the echo time. TE, equals 2 tau. And that's the same thing over here. So this is tau here, and another tau there. It's easy to sort of forget where you are when you're looking at these graphs. So here's the TE. Okay, and then we've got one more time here, which is the time, this time from which we're going to need to know. Oops. So that's going to be one of our Bloch equation times, and that one is TR minus TE over 2. So that's TR minus tau, because we're starting from the middle, TE over 2. So we're starting from this point over here, and so whereas TR goes all the way back, all the way back to here. So let me just put that in. So this guy all the way here is TR. This guy is TR minus T2. Okay. Still on the board, just barely. Perfect. Okay, so now let's work through the equations. And so the first thing is on the homework. So the first thing is, so number 1 equation is there, which you're supposed to figure out. So that's the homework problem 2. And so what is that equal to? So that's equal to, so here what we want is the mz. And so that mz is equal to mz0 times 1 minus 2e to the minus tr minus te over 2, that's tau, divided by d1 plus e to the minus tr over t1. Okay, so that's the one you're supposed to figure out, like derive that one. And how do you do that? Well, you're going to start from 0, you're going to do a negative here, and then you're going to have to plug this number in to recover, and you're going to have to take into consideration you're starting with some, so there'll be a second Bloch term to plug into over here in addition to the first Bloch term, and then you get this number. And so to derive that, you just have to do like what I did on the inversion recovery one. Just list the equations that in order that you use to figure that one out. It's not too hard. It's got about 5 or 6 steps. Okay, so now that's number 1. But what we really want is what is the size of the signal going to be right here when the echo occurs? And after we've turned the magnetization into transverse, it's going to now experience T2 decay. And so what do we... if we look for the amplitude of the echo, so that's the... So this guy was the Z magnetization, but once we've turned it into transverse, so this guy is the amplitude of the echo. And so what we're trying to do is figure out this number there. And MT record, remember, is, so this guy is, this guy is ML. But the RF record is transverse. So I go back and forth sort of drawing, sometimes longitudinal, sometimes transverse. And so here's the amplitude, amplitude of the echo, that's transverse. And what is that going to be? It's just going to be this thing. It's going to be the solution to the Bloch equation for T2. And what is that? Well, it's exactly the same thing as this minus TE over 2, which is tau divided by T1, the whole thing divided by T1 plus e to the minus TR over T1. But now we're going to use the solution to the Bloch equation for T2, and what is that? It's just the starting magnetization. It's the MXY 0 plus. So this whole thing is the starting magnetization just times e to the minus TE over T2. So, did I do that right? No, it's going to be typo. Where's my... Shouldn't that be TE over 2 over T2? Because it's... Yeah, and I think that should be... minus TE over 2 over T2. Yeah, because it's just the... Oh, no. No, sorry. See? See how easy it is to confuse Marty. Okay, so it is this time. It's not tau, it's not TE divided by 2, it's the total time to the echo. So we are interested in this amount of time right here. And so that's what we've substituted in for the, T. Because if you look at the solution to the Bloch equation, it's got a T in it, but the TE is the T is TE. Okay, so that so now that's kind of looks like a bit of a mess, and so there's a way we can sort of simplify it. So if we assume that the TE is a lot less than that means a lot less than the TR. So, and that's generally true. So, the echo time is like a tenth of or 20th of a second, and then we've got like 3 seconds or something for the TR. Then what we can do is we can assume that we can just throw out this guy. So, toss that. So if we toss that, then we can simplify the equation. And so here's the only equation that you should really, try to remember or see how it actually works, which is the equation for what the contrast is going to be in a SpinEcho scan. And so it's 1 minus e to the minus TR over T1 times e to the minus TE over T2. So that's our final answer. And so now let's look at that and sort of see what it tells us. So this is the main result. So what does it have in it? So it's got tissue properties in it. So what are the tissue properties? So the tissue properties, this is basically the proton density. That's just the number of protons times the Tesla. That's what the MZ0 is. So that's the proton density. And then here's another tissue property. What is the T1 of this particular tissue? And then here's another tissue property. What is the T2? Not the T2 star, what is the T2 of that tissue? So you can see we've only got one number over here. Hence the problem, like T1 weighted or T2 weighted. So we've got 3 different things that can change in the tissue, but we only have one measurement. It's clearly not enough. So, how would you actually figure out what the T2 is? You're going to have to do you need some additional equations because we only have one equation and three unknowns. But the other thing to keep in mind is, what are the knobs that we can fiddle with? And so the knobs that we can fiddle with on the scanner is we can, change the TR and we can change the TE. So these are, knobs on the scanner. So you want to distinguish those that can adjust what our signal looks like. And those are the ones that we are going to try to figure out, what is the optimum setting to give us a large amount of T1 contrast or T2 contrast. And so the value of these equations is they sort of bring everything together, all the, what is your signal going to be? This is your signal amplitude. So what does that mean? That just means it just means image, image voxel brightness. That's what it means. So it's going to be how bright is that voxel in the image. And then you've got three different things that characterize the tissue, proton density, T1 and T2. And then you've got two knobs. So you got one data point, two knobs, and three things. So you can see it's clearly what you would call underdetermined. You don't have enough information to figure everything out. But what you could do is you could set things up in order to emphasize T1. So let's just take an example. How would we emphasize T1? Well, we don't want T2 in there. And so how do we get this term to be almost 1? We get this term to be almost 1 by having a short TE. So if we shrink the TE down, we can get rid of the differences in the images due to T2. So if you make a short echo time, and then you'd have a better chance of seeing T1. But you need more than just a short echo time, because if you look at this, we didn't recover all the way. So we didn't recover all the way. That's good, because what if we had recovered all the way? If we had recovered all the way, say we waited 6 seconds, then there would be no contrast difference between the tissue types. So in order to get a T1 weighted image, we need to have the TR be relatively short, like a second or something like that, so that there's some contrast difference. Like here's imagine another guy that's not recovering nearly as good, like that. And so that there's a difference between those two tissue types. So we definitely want to have a TR that's not too long, so that we can get a difference between the tissue types. And you could imagine the same thing if we want a T2 weighted scan. Well, then we don't want any T1 weighting, so we're going to have to make a long TR so that everybody recovers back up to MZ0, and then a relatively long TE so that there's some difference, some chance for some difference to develop. And so that's the value of going through all this mess. You get down to the bottom line. This is the bottom line, and this basically explains, how to set your knobs on the scanner in order to make, to emphasize T1 in the image, or emphasize T2 in the image, or emphasize proton density. You might want to actually measure this guy, in which case you want to do, a relatively long TR so that everybody recovers, so there's no T1 contrast, and then do a short echo time so that there's no T2 contrast, and then you could just find differences in proton density. Okay, in the last negative 17 minutes, any questions about this? So I hope I'm inspiring you to see, there's some mess involved, but then you get down to the bottom line. The bottom line is not very difficult. Physicists and mathematicians always come up with a bottom line, a useful bottom line. So I got like 5 or 6 parts, not too bad. Okay, so that was Inversion Recovery and SpinEcho with an actual echo. So it's sort of similar to what we did what I did on this, when we were going over the SpinEcho equations, but that was just for basically for this part. But now we've had some preparation and a previous echo, and we got to sort of build that in. And when you do that, then you get to something a little more complicated, but still not too bad. And it would be more complicated if you didn't have a 90 degree. If you didn't have a 90 degree, then there'd be a whole bunch of sines and cosines in here. It'd be kind of a mess. But we'll just stick with the simple 90 and 180. Okay, all good. Questions? Okay, so we'll see you on Friday, bright and early.